Here is another physics practice problem that you probably can't read because I printed it out too small, and I didn't finish, I didn't format the latex equations right there, so I'm sorry. That's okay, I'm going to read it to you. It's not a big deal. Poorly designed yo-yo is a metal disc with a radius of 0.02 meters and a mass of 0.05 kilograms. The yo-yo sits flat on, so it's not rolling. I'm going to draw a picture. So they can both freely slide and rotate. A string's wrapped around the terrible yo-yo, and a person pulls with the force of 0.4 newtons, and the center of the yo-yo moves 0.2 meters, but the hand moves a distance of 0.3 meters. So I made a little analog here. Here's a roll of duct tape. So what's going to happen is it's frictionless like this, and it's solid. And so as this is pulled, notice that it's going to unroll like that. So it's going to move. Actually, this works out pretty well. And unroll. Okay, so the distance the hand moves and the distance the disc moves are different. So let's draw a picture. So here's my yo-yo, a terrible yo-yo, in the starting position. And there's a force like that. And I'm going to put a point right there. So I have 2 points. I have the distance the center moves and the distance so this is going to move, the center is going to move over here and it's going to rotate. And the force is going to be now here. That's a vector. Does that make sense? So it moves and this comes unrolled. And so I have a mass of 0.05 kilograms, a radius of 0.02 meters, and then this is 0.2 meters, and this is 0.3 meters. Okay, got it? First question, what's the speed of the disk? So if it starts from rest, we'll call this V1 equals 0. And we don't have to do this as a vector, but I'm just writing it. So then what's the speed over here? V2 equals. And let's call this the x direction and the y direction. So we're dealing with distances, so we want to use the work energy principle. So the work energy principle says the work is the change in energy. But we need to pick our system. If I want to, and in fact, in this problem, I'm going to pick two systems. In the first case, I'm going to pick the point particle system consisting of the yo-yo. When I pick a point particle system, I'm going to treat this yo-yo as a point. It has no dimensions and it can't rotate. And if it can't rotate, then the only kind of energy that I can have, the only kind of change in energy is a change in kinetic energy of the center of mass. Center of mass. And the work done is going to be the force dot the displacement of the center of mass. And that's true for a point particle system because it doesn't matter that the force is applied at different locations because it's not a rigid object, it's a point. If I do this, then I can find the velocity of the center mass right here, and that's what I'm going to do. But right here, I'm going to use this distance. So let's write this out. The work is going to be F dot delta R. That's just going to be equal to, I said F, the magnitude of F is 0.4 newtons. So in this case, let's call this, I want to write this as symbols because I don't want to put in the numbers yet. So let's call this S1, no. Let's call this D for the distance traveled, and this is equal to S. I know that's dumb, but I'm a petty person sometimes. So now I can write this as FD. That's the work done. It's the distance that moves. We can put in D as 0.2 later. And that's going to be equal to the final kinetic energy, 1/2 mv2 squared, minus the initial kinetic energy, 1/2 mv1 squared, and that's 0. So now I can solve for V2. V2 is going to be equal to the square root of 2fd over m. And we can put in our values. I'm actually going to use a calculator because I know you guys like calculators. Everyone likes a calculator. So let's just put this in. Clear square root 2 times 0.4 Can't see that. That's the force times the distance at point 2 times 0.2 divided by the mass, 0.05, close parenthesis, equals 1.79 meters per second. Got it. The next question says, if the moment of the inertia of the yo-yo is $I equals slash frac, curly bracket 1, curly bracket 2, MR hat 2, $, that's latex code, not the dollar signs. What's the angular velocity of the yo-yo? So here this says, if the moment of inertia is 1/2 mr squared, what's the angular velocity? Okay, so let's go back over here, and if I deal with the system of the real system of the yo-yo, in this case, I can have the change in energy is going to be the change in kinetic energy of the center of mass plus the change in rotational kinetic energy. I should call that lowercase r. I don't know. And so rotational kinetic energy is 1/2 I omega squared. So that's what I want to find. Now, if I'm dealing with the real system, then the force is going to be equal to, the work is going to be the force dot the displacement of the force, how far the force moves. And so in this case, that's going to be Fs, right? Because it's how far the force moves from here to there, 0.3 meters. So it moves further. So let's write this out. The work is going to be Fs, and that's going to be the change in the rotational kinetic energy, which I'm just going to leave as this, which you'll see why in just a second. Delta Kc, that's the change in kinetic energy of the center mass, plus 1/2 I omega 2 squared plus minus 1/2 I omega 1 squared. So the initial angular velocity is 0. That's fine. I have I, write it again, 1/2 mr squared, and I want to solve for omega squared. Now, I could put in values for this, but I'm not going to, because look over here. Fd is the change in kinetic energy. So I'm just going to put the change in kinetic energy as Fd. So this means I have Fs equals Fd plus 1/2 I omega squared. Let's subtract that from both sides. 1/2 I omega squared equals F times S minus D. And you'll notice that S is greater than D, so this is a positive number. I have that. Let's go ahead and put in our value for I. So I have 1/2 mr squared omega squared equals F S minus D. And then I'm going to divide by all that, so I have a 1/4. So now I have omega squared equals 4F S minus, parentheses, S minus D all over mr squared. And then so omega is just the square root of that. Let's see if we can put this in the calculator. So if I remember my values correctly, clear. So I think I remember 4, square root, 4 times F was 0.4 times S minus D is 0.1, right? Because it's 0.2 and 0.3. So I'm just going to put 0.1. 0.1 divided by, and I had to put another parentheses here, the mass was 0.05. 0.05 times the radius, 0.02 squared, close parentheses, equals, and I get 89.4 radians per second. And that seems a little bit fast. Let's just convert this to, let's do this the old-fashioned way and convert this to our degrees per second. Let's just do degrees per second. So if I multiply this by 180 degrees over pi radians, then I'll get this in, oh, that seems really fast. Okay, so times 180 divided by pi. So, ooh, super fast. 5, 1, 2, 5, degrees per second. Okay, well, how can I fix this so it's not so bad? What I need to do is to not let it unwind as much. So if I change this problem, and I think I will when I give it to students, s, if s is equal to 0.22, then that distance will be much smaller, and this will be much smaller. So let's use that, meters. But still, I'm not a number person, right? I like that. I like that answer. This does say the harder you pull, and the greater the change in distance, the greater the angular velocity, which makes sense. All right.